A very good afternoon to all of you, and I hope everybody is fine. I hope everybody is enjoying. And today I'll be talking about Pauli's exclusion principle. And before actually going into some mathematical description of Pauli's exclusion principle, it rather will be more precise if I talk about the applications of this principle. So, starting with an argument, starting with the statement of the Pauli's exclusion principle that no two fermions, what fermions are those particles which obey Fermi-Dirac statistics. Fermions are the particles whose spins are in the fractions of half. Neutrons, protons, electrons, they all fall in the category of fermions. So the statement of the Pauli's exclusion principle is that it is not possible for two fermions to occupy the same quantum state. Rather, there is another way of expressing the Pauli's exclusion principle, and that is that you cannot have two electrons in the same quantum state having all the four quantum numbers equal to each other. So if you have two electrons, say for example, in the same quantum state, they cannot have all the four quantum numbers same. Even if their first three quantum numbers are same, the last one, which is the spin quantum number, that has to go against each other. Now, so this is the argument of Pauli's exclusion principle. This is what this principle states. So this Pauli's exclusion principle, it certainly has its triumph applications in atomic structure and in drawing out the elements in the periodic table. So electronic configuration can be executed using the arrangement of electrons in the orbitals of the atoms by exploiting the statement of Pauli, what's called as Pauli's exclusion principle, and automatically it certainly becomes a very, very fundamental tool to understand the chemical reactivity of the atoms, that why atoms react and why they form bonds, why they form different kinds of bonds. The Pauli's exclusion principle plays an exclusive role in demonstrating the chemical properties of these atoms. Then there is another field of science, field of physics, and that's what is condensed matter or solid state physics and semiconductors. Pauli's exclusion principle, it certainly becomes a basis of explaining the band theory of the solids. Now, what is the band theory of the solids? Tells us that why certain materials are conductors, why certain materials are semiconductors, and why the other materials are insulators. So you cannot design the bands, because when you think of using Pauli's exclusion principle, it certainly imposes restrictions on filling the atoms in the atomic orbitals. So the filling of atoms, the filling of electrons in the atomic orbitals leads to the formation of valence and conduction bands, by virtue of which we can differentiate, we can classify solids based on the band theory of solids. So Pauli's exclusion principle is a key. It's a key tool in designing, in understanding the formation of bands in the solids, which automatically lead to the formation of, to actually classify that whether a material is a conductor or a material is a semiconductor or it's an insulator, based on filling of these atomic orbitals by the electrons in a solid matter. And, and, and obviously the same argument fits for the conductivity. It explains why there is conductivity in the metals and why you have materials which do not conduct electricity when you're applying the potential difference across those materials. So it has a very, very strong role in the field of solid state physics. Then, if we go into the domain of this research of material science, where the modern world is performing all around in terms of developing these quantum dots and the nanotechnology based on these quantum dots, the exclusion principle plays an influential role, because when you go to the quantum level, when you go to the quantum state of the material particles, on account of synthesizing these particles, so exclusion principle becomes a very strong tool to ascribe those energy bands that form when you go to the quantum, when you go to the designing of the quantum systems. Because if we talk about the bulk systems, they all work with the classical laws. And here, when you go to the nanoscale of the materials, you have a transition, and you have energy gaps. And these energy gaps come in action, and the existence of these energy gaps can be explained by actually filling up the electrons in the orbitals in accordance with Pauli's exclusion principle. So it influences, you can understand the optical and electronic properties of these quantum dots, and talking about the tunneling phenomenon, where electron cannot occupy the filled states. I mean, electron has a probability of getting tunneled from a barrier which is not possible in the classical domain. Another important application of exclusion principle comes in the field of superconductivity. As we know that we find certain materials. The first one was probably mercury, and mercury was it was Gamerling-Ons in 1916. He was basically investigating the resistivity properties of mercury at low temperatures. And what happened, accidentally, he could measure no resistivity in case of mercury when the temperature reached close to 4 Kelvin. So to explain the phenomenon of superconductivity, what we do is we introduce the concept of Cooper pairs, and what a Cooper pair as a whole is, it's a boson, but the particles who take part in this Cooper pair, they are electrons, they are fermions. So it seems like that Pauli's exclusion principle becomes a key to explain the phenomenon of formation of the Cooper pairs, where the electrons bump on each other irrespective of the repulsive force, because the repulsive force between the electrons is overcome by the lattice strains that are developed in those materials at very, very low temperatures. So once a situation is created, the electrons bump on each other in the context of exclusion principle and form a Cooper pair, and Cooper pair is basically a boson. So Pauli's exclusion principle, it certainly plays plays its own role in describing the phenomenon like superconductivity and superfluidity in helium atoms. And we can also extend down the application of exclusion principle in the field of astrophysics and stellar evolutions. If we talk about the white dwarfs, as we understand that if we have an old star, and when this old star runs out of fuel, when it runs out of hydrogen, maybe all of the hydrogen it possesses is gone translated into the helium atom and emitting a lot of energy at the same time. There's a well-known phenomenon that happens to the star, what's called as supernova. So once there is a supernova, there's an explosion, and the explosion that we have leads to some kind of contraction in the core of the star. Now, this contraction, it has some mathematical background that can determine whether this star will convert into a white dwarf, or it will convert into a neutron star, or it will convert into a black hole. So what's generally called as Chandrasekhar limit. What we have here is talking about white dwarfs and neutron stars. They don't collapse. There is no collapse of the whole of the star. The collapse is restricted by what's called as degeneracy pressure. And the origin of this degeneracy pressure is the Pauli's exclusion principle, because you have a limitation of filling up your orbitals in the atoms. So that limitation leads to the formation of white dwarfs and neutron stars. And this Chandrasekhar limit, it certainly explains us that why in certain limit we have a white dwarf, and why in certain other limits we have black holes. The point is that even though there is an explosion, the star tends to collapse, but it does not collapse to the singularity. There's the birth of the inward pressure, and this inward pressure is the result of that degeneracy, and that degeneracy is the result of the exclusion principle that I'm talking about. So it has the applications in population inversion of lasers. What it does basically, it enables laser operation by electron transitions, and it's the exclusion principle that does not allow electrons to remain in the same quantum state. So if the electrons cannot remain in the same quantum state, there is every possibility of creating a population inversion in those states. Quantum computing, the world is running towards quantum computing, and we know that we have qubits. We can have qubits of these Cooper pairs. We can have qubits of ions. We can have the spin qubits. The precise manipulation of these quantum states are dictated by the Pauli's exclusion principle. Then it has a very beautiful role in nuclear structure and nuclear reactions, as it has a beautiful role in atomic structure and atomic reactions, as we talked about. So it's a key postulate in the domain of nuclear shell model, and it determines protons and neutrons, the arrangement of these fermions within the nucleus of an atom. And last, this is not the last, I mean to say the last slide that I have, they may have a long range of further applications, but it certainly plays a very important role in understanding the quantum nature of magnetism in magnetic materials. And we can understand magnetism and antiferromagnetism, spin alignment, governs these properties, and certainly there's a role of Pauli's exclusion principle in demonstrating the quantum nature of magnetism. So these are some of the important applications of Pauli's exclusion principle. Now, what seems to be important is, now I would like to go with some, it's happened, I don't get this, I'm not able to close it. Okay, I can keep it here, let's see. So, what we're going to talk about is Pauli exclusion principle. So, previously I talked about the strongevity of this principle, and you couldn't find a field where you cannot make use of this Pauli's exclusion principle, which states that you cannot have a quantum state which can accommodate two electrons in such a way as if all the four quantum numbers of both electrons is same. Now let's try to analyze this exclusion principle in a mathematical way. So let me suppose that I have a state psi of say psi of A is a state, and this state has two particles, and say I have the particle R1, I have the particle R2, and this state can be represented as the multiplication of the two states, psi of R1 and psi of, I should use psi of A and psi of B as an exchange R2 and R1. All right, so I have two particles, and I try to write down these particles as a quantum state, say psi of A with particle 1 at R1 and R2. These are all probabilities, psi A R1 and psi A R2. Okay, and I think I should come up with psi. I shouldn't use a subscript here. I should introduce it. This is psi of AR1, psi of AR2, and if I exchange the two particles, R2 and R1, then I will have psi, I should call this the state B now. So I have two states, psi A and psi B. So here in the A I have R2, and in the B I have R1. Now, what is important here is that two electrons, they have the same faces, they are purely identical. You cannot differentiate one fermion from another fermion. They are identical. And what you are doing is, you are writing down the wave function. You are writing the state of the two particles. Whether you write the state of the particles as psi R1 R2, or you write psi R2 R1, it doesn't make any difference. It doesn't make any difference when you calculate the probabilities. The probability of finding the particles in terms of psi R1 R2 must be equal to the probabilities of the particles that you can find in terms of psi R2 R1. So what does that mean? That means this psi of R1 R2, it's more of scatter, what's called a Born approximation. The probability of finding these particles R1 R2, it must be equal to the magnitude of psi of R2 and R1. So the exchange is there, but you cannot differentiate the outcome of the experiment. If you measure the experiment, the results that you will obtain in terms of R1, R2 would be same. The probability will be same in terms of R1, R2, and on exchange R2, R1, the probability is going to be same. So what does that mean? That means this psi R1, R2 is plus minus psi, this is psi R2, R1. So what is introduced here is the two signs. We have the plus sign and we have the minus sign. We have the negative sign. These are the two signs. Now, if I obtain my wave function as, say, that is psi, and this wave function comes out to be 1 by under root of 2 times psi A R1, psi B R2 plus psi A R2 and psi B R1. And don't be confused about this 1 by root 2. This comes out as a normalization constant. And the psi, if the psi is 1 by root 2 times the addition of the two products, then this psi is a symmetric wave function. It's a symmetric wave function. And what does the symmetric wave function means? The symmetric wave function means that if you exchange this type of particles, they're not going to change the sign of the wave function. On exchanging the two particles, if there is no change in the sign of the wave function, then what you say is you call this psi as a symmetric wave function. And you have a category of the particles that obey this condition, that obey this symmetry. That category is the category of the bosons. And photon is an example of bosons. So if you have two photons and you exchange the two photons, on exchanging the photons, the sign of the wave function does not change. So it means there's no restriction on the number of photons that can be accommodated by a same quantum state. So if you have a quantum state, it can accommodate infinite number of bosons. And the Bose-Einstein condensation is a result of this conformation of the quantum mechanical interpretation leading to a symmetric wave function. You're exchanging the particles, there's no change in the wave function, no change in the sign of the wave function, then this is a representative of, this is indicating that the particles that you are dealing with, these particles are bosons, and you can have more than one particles that can be accommodated by the same quantum state, by the same quantum regime. Now, the next thing that we have, so what we have here, we have psi s. And we can boil down the same thing to psi anti-symmetry. And psi anti-symmetry comes as 1 by under root 2 of psi A of R1, psi B of R2 minus psi A of R2, psi B of R1. So when you exchange the particles, if your wave function comes up as negative, that means there's a restriction. There's a restriction on the number of particles that can be accommodated by the same quantum state. And how can we demonstrate this from this equation? Now, if I assume that both the particles, the particle 1 and particle 2, if they're accommodated by the same quantum state, then what will be psi as? So the first important thing, if psi as is negative, it's a pure indication of the the anti-symmetry of the wave function, and it's a pure indication that you are talking about, you're dealing with the particles like fermions, and fermions are electrons, fermions are neutrons, protons. They fall in the category of fermions, and fermions obey the statistics, and that statistics is called Fermi-Dirac statistics. Now, if you have both the electrons in the same quantum state, then can we measure the wave function for them? And the answer is no. So this is 1 by under root 2. So you will have psi A of R1, psi A of R2 minus psi A of R2, psi A of R1. So the 2 will perish, and the wave function that we will obtain, the wave function is 0. Now, if the value of the wave function is 0, the probability of calculating the existence of the two particles is 0. But that does not mean that there are no particles. We started with two particles. There are two particles that are existing in the quantum system. But if you assume mathematically that the two particles occupy the same quantum state, then you are not able to calculate its wave function. So automatically, you're not able to calculate the probability density of these particles. So with this is an indication that this becomes the basis of what is called as Pauli's exclusion principle, that no two particles can occupy the same quantum state. Or in other words, we can say that if we have two electrons in the same orbital, they will not have all the four quantum numbers which will be same. At least one of the quantum numbers that's involved has to be different. They cannot accommodate exactly the same quantum state. And the basis of that argument is this quantum mechanical description that we have tried to give here. So we can think of examples. If we have an atom, say for example, with two orbitals, say this is 1s orbital of any atom. If this is 1s, now for this electron and for this electron, n is equal to 1, say, and for this orbital, L is equal to 0. So if L is 0, ML is 0, and MS has to be plus half. And for this particle, N is 1, L is 0, ML is 0, and MS is minus half. So we can see that the fourth quantum number, which is called as spin quantum number, that is exactly opposite between these two particles, if these two particles have to be in the same atomic orbital. So this is how Pauli's exclusion principle works, and it works in almost all domains of quantum physics, and it's a very, very strong tool in the world of quantum mechanics.